We're about to dive directly into the proof of this proposition. The proposition, it says this only, but as it happens usually often in mathematics, it's sometimes easier to prove something stronger than what was stated. So again, m of t is defined as the expectation of e to the tx. And what we're going to prove, which is stronger, is, and we assume that m of t is finite for t in this interval. And what we're going to prove is that the derivative with respect to t, the kth derivative with respect to t of this function, m of t, this equals to the expectation of xk times e to the tx. Well, as you have noticed at this point, I'm not a very big fan of unnecessary parentheses, but here we have expectation, a random variable, another random variable. It's not clear what is being integrated, so here we do need parentheses or brackets. So it's the whole product which is being integrated. So we're going to prove this, and we're going to prove this by induction on K. On K. So we need the base case and we need the induction case. So for the base case, let me not take k equal 1 because it will be the same work to prove for k equal 1 than to prove the induction case. So it would be doing exactly the same work twice. Let's start. Let's be smarter than that. And instead, let's start with k equals 0. When k equals 0, there is nothing left to prove. There is nothing to prove at all. What is the 0th derivative of a function? Is just a function. So m, the function itself. Well, x to the 0, this is just 1. And this is what we have to prove. But, well, there's nothing to prove. This is the definition of m. So the case k equals 0, it holds. And now we're going to do the induction. So we suppose it holds for some fixed n. So suppose it holds for some k in this set n. Well, here we need to also allow k to be 0. So let me put n0 here to be very careful about it. And, well, now what we have to do, we have to prove that identity. And we're going to do the following. Let me define this function, this random function. Well, it's not random. That's the point. It's a function that has a parameter and an argument. And this function is a g. It's a function. It has x as a parameter, and it has t as an argument. And let's define this function as follows. Define it to be x to the k e to the tx. That's strange definition, but you can see it matches what we have and where we're going. So we see here, if we take the derivative of this function, and that's why I'm writing x as a parameter and t as an argument, because when we talk about derivative, it's clear we're differentiating with respect to the argument. So the derivative of this function, well, we know what this is. This will be x to the k plus 1 e to the tx, because we're differentiating with respect to t. And now what we can write here is the following. Let's write the derivative with respect to t of the kth derivative of the moment generating function, which by assumption, because we are supposing this assumption holds for k, so it is exactly the expectation of what is here, which I can write directly as g with a random parameter and having t as the argument. And now how can, if we take the derivative of this, and well, indeed we have the derivative. Let me do some magic here and reinsert the derivative that was missing. Now, so what is this? This is, if we could now commute and enter the derivative, then this would become the expectation of the derivative of g, and we know what's the derivative of g, and this would become the expectation of x to the k plus 1, the exponential of t times x, which is exactly what we are trying to prove. We supposed the claim holds. We have supposed the claim holds for k, and now we are proving it holds for k plus 1, but we need to justify this part here, and this part will be most of the work. So what is the derivative? How do we write the derivative as a limit? Well, we take some age n, some sequence age n that goes to 0, as with n, as n tends to infinity. Well, tends to 0 from above, of course. And then we want to study what is g x of t plus age n, minus g x of t, and divide this by age n, and take the limit as n tends to infinity, and see that if the expectation of this will converge to the expectation of what is the derivative of this. So for each x fixed, this we know what this converges to. This converges to exactly x to the k plus 1 e to the tx. What is, so we know already that what is inside converges to that, because this is the definition of derivative. What we want to know is that the expectation also converges. And this is the whole point why we need to use those convergence theorems. So we want to be able to find a way to justify that because this converges to this, then the expectation converges to the expectation. And how are we going to do that? Well, of course, you can guess. At this point, we only have 3 theorems to work with. One of them is Fatou. It is very general, but doesn't help us make many conclusions because it doesn't assume functions converge, etc. The other one is monotone convergence theorem. It requires things to be monotone and non-negative. These things are neither monotone nor non-negative. So we're going to really to use our powerful nuclear weapon, which is dominated convergence theorem. We're going to show that this part here is dominated by something which is integrable, that does not depend on n, and then we can apply dominated convergence theorem to say that this expectation converges to this expectation. So this is what we have. This is the definition of this function g parameterized by x with argument t, and this is what we have to prove. So as we discussed already, we want to find an upper bound for the integrand here in order to apply dominated convergence theorem. And what we can notice is this here by the mean value theorem. So what is this? This is the slope of the tangent of a second line. This is, we have the graph of gx. We take 2 points, they're different points, even if they're very nearby. We compute the change in g, we divide it by the change in t, and this is the slope of a second line, and this is the classical definition of derivative, as it's the slope of the tangent line as the limit of slope of second line. But what we have the mean value theorem. The mean value theorem, it says that gx of t plus age minus gx of t, if we divide by age, that's the slope of a second line, this equals g prime x of some theta. And what is theta? Well, the mean value theorem doesn't say what theta is. It just says there exists theta. And where is theta? Theta is between t and t plus h. Theta is in this interval. So there exists theta with this property. What we need to be careful about is that this theta, it depends. It depends. It may be clear here from the way it is written, but let's be explicit. It depends on x, t, and h. Okay. But now what we do is we are in this interval. We are in this interval from minus epsilon to epsilon. We have our t is inside, which means our t, it is at some distance from epsilon, a comfortable distance. So let's take some delta even smaller, such that this is still comfortably within the interval. This would be t plus or minus delta, this interval here. And now what we notice is for age less than delta, we have, so what is g prime of theta? G prime x of theta. Well, just look what g prime is. G prime, it is x to the k plus 1. It is e to the t theta times x. And now we want to find an upper bound for this. We want to apply dominated convergence theorem. So what we really want is to take the absolute value here, which is the same because these two things are equal, the same as taking the absolute value here, and find an upper bound for it that has that does not depend on n and that has a finite expectation. So let's put an upper bound here, upper bound. So how can we make an upper bound for this? Well, this, we can put it here. And this here, instead of theta and x, let's replace theta by, epsilon minus 2 delta. Okay, so epsilon minus 2 delta is still here at this distance. And well, let's then put the absolute value here on x as well to make sure this really is an upper bound, because in case x was negative or etc. Okay, so, and now we can make a bound. This is bounded. What is this? This is a polynomial, or something that grows like a polynomial. This is some exponential. So we can always increase a little bit the exponent here, and the new exponential will dominate this polynomial part. So this is an exercise for you. This is a calculus. This has very little to do with measure theory or probability theory. Is if we give up a little bit in the exponent here, then we can beat this constant, this polynomial term for very large values of x. For small values of x, we need to accommodate that. We accommodate that by putting some small constant here, some big, large constant here. So there's a large constant that we can put here, and this will become exponential. Then here we have epsilon minus delta. Okay? From 2 delta, we went to delta. That's how we can get rid of this term. Epsilon minus delta times the absolute value of x. And this is true for every x. That's the important thing, that this is true for every x. It is important that this is true in every x, for every x, even though the constant c itself depends on epsilon and t. So this is true for every x. So we can now make the bound. This bound here, if we replace little x replace it by capital X as a random variable. So this becomes capital X, this becomes capital X here. And this random variable, this one is integrable by assumption. Let's link it back to our assumption. This random variable is finite. Its expectation is finite by our assumption. This concludes the proof that moment generating functions can be differentiated. This concludes this video lecture.